Hello, everybody. We are here again in our Graduate Studies Symposium. And this afternoon, we have Dr. Laurence Rilett. who is a professor of civil engineering at the University of Nebraska-Lincoln. He's going to talk to us about the COVID-19 pandemics and the transportation system. Professor Rilett also is the director of the University of Nebraska-Lincoln Mid-America Transportation Center, and he's also a director of the Nebraska Transportation Center at the university. And for 2020 and 2021, he's the vice president of the Council of University Transportation Centers in the United States. I know Professor Rilett for a long time. He did his undergraduate and master's studies at the University of Waterloo when I was there. It was when I met him for the first time. And then he went to do his PhD at Queen's University in Canada. And since he finished his PhD, he's been a professor at the University of Alberta in Canada and Texas A&M University in Texas. And currently he's at the University of Nebraska-Lincoln. And he's also registered as a professional engineer in the state of Texas. He's taught several undergraduate courses and graduate courses in statistics, risk analysis, traffic engineering, transportation planning. He's a great teacher. We had the opportunity to discover that when he visited San Carlos as a visiting professor several years ago. And he's been collecting awards on teaching and research over the last 25 years or so, or maybe even before that. He's published over 90 papers in journals and over 90 conference papers. His field of research is transportation system analysis, and his research is divided in two main areas: intelligent transportation systems applications and large-scale transportation systems modeling. He has led over 40 research projects since he started as a researcher, and he's received a total funding of more than $45 million. Currently, he's also the managing editor of the American Society of Civil Engineering Journal of Transportation Engineering, Part A, and he's also in the editorial board of the Journal of Intelligent Transportation Systems, Technology Planning and Operations. I think I already spoke too much, and I'll let Professor Rilett to go on with his talk. Thank you, Larry, for accepting our invitation.
Great. Thank you, Dr. Sethi. So it's my pleasure to be here to talk to you today. Jose, can you confirm you can see this okay? We good?
Yes, we can. Yes, we can
Perfect.
see it fine.
Okay. So by way of background, I'm going to talk briefly about my experiences at Nebraska Transportation Center and Mid-America Transportation Center, just basically give you an idea of how the U.S. organizes its transportation research. Then I'm going to go into the main part of my talk, which is on the COVID-19 impacts on transportation. I'm going to focus on two parts. The first part is an overview, a broad overview of what went on. And then I want to go into a little bit more detail on some of the work we've been doing on travel time reliability and how the COVID-19 pandemic has affected that. And then I'm going to end with some future thoughts on how we measure system performance. And given that, we'll start into the first part, the overview of transportation centers. So as Dr. Sethi indicated, I'm director of the Nebraska Transportation Center. It's sort of unique in the United States. Canada doesn't have a lot of these, but they're a way of getting people that are in the same area but in different departments or colleges together. So it's a very North American perspective and really a U.S. perspective. These centers are research focused. They're not degree related, so we don't give a degree in transportation. For example, I'm in the Department of Civil Engineering. Some of my colleagues are in the Department of Mechanical Engineering. but it's a way for us all to get together and do joint research and joint teaching. As Dr. Setti indicated, I'm Vice President of the Council of University Transportation Centers. We have 85 centers in our council across the United States. So almost without exception, every university in the United States will have some type of transportation center that's related to this. You may have heard of some of them: Texas Transportation Institute, Pennsylvania Transportation Institute would be some of the larger ones in the United States. They're very multidisciplinary, lots of different groups. We have engineering, civil, mechanical, we have business faculty involved, we have arts and science, particularly statistics, cognitive psychology. We work very closely with our medical centers. The other thing that's unique about these centers is that they're all soft money. The university does not provide us money. We go and write proposals and compete for research. And basically what we end up doing is the research that we get funded is the research that we do. To give you some background information, our center's been around since 2006. We've conducted over approximately 370 projects with funding of about 90 million. Right now, we have 93 active projects with funding on the order of 32 million. It's very difficult to compare money across countries. You know, $1 million in the US is different than $1 million in Canada, is different than $1 million in the United Kingdom. But we always look at it, I always look at, well, how many students do we have involved right now? So right now we have about 50 graduate students in our center, all receiving funding. So typically we would call this a research assistantship. The students would get tuition, they'd get a stipend to do the work, they get health care. We also have 32 undergraduate students working in our field. And the work that we do, these projects are very broad in scope. So it's things that I do: transportation systems, we have structures, we have bridges, we have people doing pavements, we have people looking at computer science applications, communications, connected vehicles, all of these types of things. Anything that's related to transportation, we typically would have faculty involved doing those types of work. At our center, we have a number of core facilities. We actually have a crash testing site, the Midwest Roadside Safety Facility. So we do a lot of roadside barrier work. If you're a fan of NASCAR or IndyCar, and you see the barriers on the side of those race cars, you would see something that was developed at our center. On the bottom is our ITS lab, our traffic lab, where we have a focus on safety and operations. We have 3 test beds where we get continuous amounts of data from these test beds, both on the railway, arterial, and highway. I'm going to be talking about some of the data that we used today came from our ITS lab. So we have a fiber optic connection to our local transportation agencies at the city and the state, and we can basically get access to any traffic system, traffic signal in our state, brought back to our ITS lab, and we can use that for research. The other thing that you may sometimes hear about is these centers that are sponsored by the United States Department of Transportation. We're fortunate enough to have the Region 7 University Transportation Center. We've held it since 2006. It brings in approximately $3 million a year to our center to do work. And you can see that the scope of what we're doing, our Region 7 is the states of Iowa, Missouri, Kansas, and Nebraska. We are the lead, but we have partners with other universities: University of Iowa, University of Kansas, Missouri University of Science and Technology, our medical centers, Nebraska Indian Community College. So we compete for this, and we've been fortunate enough that we've won this a number of times in the last few years. When you compete for these projects, you have to pick a theme. Ours is safety. In our particular, freight movements of hazardous goods, and in our case, extreme events, which in our area It's flooding and wind events is the primary drawer. We do research on how to mitigate and eliminate issues related to these extreme events on the transportation system, and how to mitigate and eliminate threats due to hazardous goods. And we have a number of projects going on related to that. I don't have any, I'm not going to spend any time talking about it, but these are fairly large projects, multi-university projects, multi-year projects, because the issues we're talking about are very, very complex. And so we always get the question, why do you have two centers? Well, the Nebraska Transportation Center is the one at the University of Nebraska. We compete for funding, and one of the things that we compete for, some of the funding we compete for, are these national centers. And in our case, we happen to have a US DOT University Transportation Center. Right now, there are 35 funded centers in the United States. And you'll see some of these sometimes when you're reading or seeing seminar announcements. You'll actually see the US DOT logo on there, and they're typically funded by the US government. We also do outreach, which is kind of unique part of our centers on the federal side. We actually run after-school programs. We've had over 12,000 students go through ours. Our goal is to get middle school students in grades 6, 7, and 8 to continue on in math and science. We have a scholars program where we bring in students from underrepresented groups to our campus, encourage them to go to grad school. We have an intern program where we take our students and put them into with businesses so they can get experience working as engineers before they graduate. We have a Sovereign Native Youth Academy where we bring high school students, Native American high school students onto campus and have them encourage them to go on and take STEM careers in transportation. So these centers that we're talking about are actually very broad. We work very closely with our College of Education on all of these outreach activities, and much different than I was used to when I started this back in Canada. Lately, we've got another center. This one's on rural railroad safety, sponsored by our Federal Railway Administration. Again, a multi-consortium. The lead is Kansas State University. We're one of the partners. If you've ever been to Nebraska, we actually have the largest freight corridor, railway corridor in the world. Some of our cities have 150 trains a day through them. These large freight trains that are about 1.5 kilometers long. So railway is very important in our region, and that's one of the reasons that we were very happy to get this center. We also worked internationally. This is a joint ITS center with India that we've worked on. The funding's gone, but we continue to work together. It allowed students and faculty to go back and forth between Nebraska and India. So that's a quick overview. I wanted to go over some of the lessons. What we're finding in the United States is that our transportation problems are getting so complex that only really multidisciplinary solutions, multidisciplinary teams can really attack them. And so that's why our centers have civil engineering and mechanical and statistics and medical and education. Is if we want to go after these large grants and solve these very complex problems, we need expertise from all sides. The other thing I wanted to get across is that we've been doing, it's very multifaceted. It's just not working with the university. We're looking with K through 12. Obviously, we work with undergrads and grads, but we're also heavily involved in continuing education and workforce development for engineers that have already graduated but are in the workforce. And the last lesson learned is just how diverse our group is. We have multi-universities involved, we have multi-colleges, but we also have the private sector, Union Pacific, the NSF, as well as the public sector, heavily involved in the work we do. What I want to do now is talk about COVID-19, so that's subject of my talk, and really look at big picture before I go into a little bit more detail on one aspect that we've been studying. So in terms of transportation volume effects, obviously when the pandemic came on around March 2020, a lot of things were shut down or taken offline. Globally, road transport activity declined about 50%. In our state, we had about a 30% decrease in statewide traffic volume. And we saw a major modal shift from public transport usage to personal vehicles. I have some slides here I'll go over. This slide shows US monthly vehicle miles traveled. This is comparing 2019 in the blue with 2020 in the yellow. We're doing second quarter, so April, May, June. The y-axis is vehicle miles traveled in millions, and again the x is showing April, May, and June. You can see there's a major drop in vehicle miles traveled, much less traffic being covered in the United States. You can see from April to May to June it started to rebound, but to this day it still hasn't rebounded totally. The biggest change you can see for April, passenger cars were down 46%, commercial vehicles were down 13%. So even the freight, which had to move, we had a drop in freight movements in the first quarter or the second quarter of 2020. And I want to just stress how big this is. So when we look at vehicle miles of travel, there's usually fluctuations from year to year. We have 1% to 2% changes. 2008, when we had a major recession in the United States, we had a decline of about 4%. With the COVID impact, we had a drop of 40% in April 2020 compared to 2019. So we're talking major changes in our transportation system. And I'll come back to this statistic in a minute. There was also impacts on other things. We can look at bike travel. And what we found that areas that aren't known for bicycle commuting, and these would be smaller cities in the United States, Knoxville, Tennessee, and Provo, Utah, doubled their bike activity during May and June. So it was both recreational cycling, but also people getting off public transit and using their bikes to travel around. Conversely, in areas that had high cycling numbers, cycling to work, they had a decline, but a much lower rate than the decline in VMT. So even the places on the coast, warmer areas, California, had major declines. This next slide I'm showing is a bike travel percentage change. Blue indicates growth, so the bigger the circle, the bigger the growth. Yellow indicates decline. The bigger the circle, the bigger the decline. And as you can see on the west coast of the United States, we had a decline in bike traffic. In the center of the country, we actually had an increase in bicycle traffic. I want to take a second just to talk about this graph. It was given by streetlightdata.com. And this is kind of new to the United States in the last 5 to 10 years. In the past, the transportation data, almost 100% came from the public sector. But with the expansion of cell phones and Bluetooth devices, the private sector has actually better transportation data than the public sector. And they've started to incentivize this. They started to collect it and sell it back to the public and to researchers. And this streetlightdata.com is actually from our cell phone companies in the US. They can collect cell phone data, they know location data. From that, they can infer whether it's a car. You know, if they see a cell phone going at 75 miles per hour on a highway, they can pretty much infer what type of vehicle it is and that it is a vehicle. They can infer from the data whether someone's on a bicycle or someone's walking, or someone's on transit. So we actually have right now a very robust data set on how people travel. And it's because of these private sector firms. And you can see from this graph how complex they can get it. They can show you changes in bicycle transportation because of a pandemic, right? And you can see that it's changed a lot. I'll come back to this. The reason I wanted to point this out is we're going to use similar data than this later on in this presentation, and I want to just point it out that these are coming from private sector sources. Federal Transit Agency showed that we had a big drop in transit. FTA showed a drop of about 85%, and we still haven't recovered. Here's an example of US monthly urban rail trips in 2019 and 20. 2019 is in red. Blue is in 2020. It's from January to June. On the y-axis is millions of trips. On the x-axis is time. And you can see we just had this very severe drop from about 400 million trips down to about 40 trips. So it dropped about 10%, again, because of the response to the COVID-19 pandemic. It's starting to slowly recover, but we're still into this drop, and the effects of this will be lasting for a while. Similarly, air volume. You can see what's happened to domestic flights in the U.S. from about 680,000 flights down to 120 by May, or sorry, 190 by May, a nearly 74% drop since May 2019. Has a very big impact on us. With the drop of 75%, we get a decrease of 50% in airport revenue and passenger traffic, 50% loss in airline seats, just amazing amounts of loss of money. So when you, in our case, in the United States, we see a lot of our federal dollars, the fiscal stimulus going to airlines and airports. And the reason is because of this. They've taken a huge financial hit. And if the government did not fund them, they would be in danger of going bankruptcy. The last thing I wanted to talk about from a big picture point of view is the fatalities and the fatality rate. What I'm showing here is the fatality rate for 100 million vehicle miles of travel from 75 to 2019. So before the COVID-19 pandemic. On the y-axis is fatalities. On the x-axis is the years from 75 to 2019. And you're going to notice a number of things. The black line shows the fatality rate for 100 million vehicle miles of travel. So you can see that in the 70s, we're about 3.35 fatalities for every 100 million miles. And that's steadily declined to 2019. So it's gone from 3.35 to 1.10. This is attributed to a lot of things: safer vehicles, safer roadways, better monitoring of the roads, less drunk driving, these types of things. So even though we have this horrific death rate, we still have about 40,000 deaths per year on the US system. The rate has gotten much better, which is a good thing. And you could say, well, why did if we're getting this big decrease in fatality rate, why are the deaths holding fairly steadily? In 75, it was 44,000. Now it's 36,000 a year, which is still way too much. And the reason is that vehicle miles of travel over time have been increasing. So even though our fatality rate's been going down, the number of miles traveled has been going up, and we're not getting as low a rate as you might first expect. And I want to come back to this way of interpreting or looking at numbers for the remainder of my talk. This graph shows some of the other things that we're finding in the United States related to COVID-19. So I've titled this one Risky Behavior. These are unbelted fatalities in the second quarter. And we're comparing 2019 to 2020. So when we record fatalities in the US, we collect a lot of data. One of them is, are they wearing a seatbelt? So are the people who died, were they wearing a seatbelt in the crash? So you can see in 2019, when there was a fatality, 18% of the people approximately who died were not wearing a seatbelt. In 2020, it went up to about 24%. And the question is, why? Okay. And one of the answers, or one of the theories, is that people, because of COVID-19, it's affecting their mental health, and people are starting to take more chances. And we're seeing this in people not wearing their seatbelts. We see this in speeds going up. In our state, it's in the Midwest. It's very rural, very small population. The number of speeding tickets have increased dramatically since COVID-19 started. You can sort of see it. The volume goes down, there's less traffic, and people start speeding. And I'm not talking speeding 5 or 10 miles over the limit. We've had people going 120, 130, 140 on our highways during this pandemic as they're crossing the state. So our police officers have actually been very busy trying to identify those people and pulling them over. So what really this graph shows is that there's this, across the US, there's an increase in risky behavior by people. They're not putting seatbelts on, and it's directly attributed to the pandemic. So what does that mean from a transportation point of view? Well, as we talked about, the traffic volume went down. And from the second quarter of 2020, we're down about 16%, including passengers and freight. Fatalities are also down, which is what you'd expect. You'd expect if the volume went down, the fatalities would go down. So we've had about 9,000 people die in the second quarter of 2020, still too many. But the interesting thing from this data point is that the decrease was only 3.3% compared to 2019. So the traffic volume decreased 16%. Our fatality rates only went down 3%. And it's attributed, what people are beginning to attribute it to, and they haven't completely done all the studies, of course, is that increased speeding, increased impaired driving, increased risky behavior. Right? So the traffic volumes decreased more significantly than the number of fatal crashes. That means our traffic fatality rate per 100 million vehicles actually went up in the COVID crisis. So we've had this steady, this 40 years of decreasing fatality rate, and now we have a bump up because of the COVID-19. Right? We're not getting the number of fatalities lower than we would expect. But it also shows you when you're looking at things such as fatality rate, what goes into it, right? It's not only vehicle miles of travel, but it's also the behavior. And when behavior changes, then you get changes such as this, that you have a rate going up. So what are the lessons learned from this sort of big picture? Well, COVID-19 had a large impact on vehicle miles travel, mode usage, transit down, bicycles can be up or down, air traffic's down, etc. I don't think I'm saying anything that people haven't read or heard about or experienced. Some things are unexpected though. We never expected the fatality rate to increase. I personally didn't think about risky behavior increasing, but it sort of makes sense when you're in these weird times that we are in right now. The other thing I wanted to point out is from a US perspective, a lot of our data is actually coming from the private sector. They have much better data than the public sector because of the information on cell phones and Bluetooth. There are actually people that can go through and actually measure COVID movements based on cell phone, right? They can see where people are traveling, and then they can connect that to COVID-19 outbreaks. So it's a different world from transportation engineers, and we get data from a large number of different places. Which brings me to the third part of my talk. I want to talk and do a little bit what we would call a deep dive into travel time reliability, or TTR. And I'm not sure about the Brazil and the other folks on listening to the talk, but this is rather new in the United States, probably in the last 10 to 20 years, but it's really taken off in the last 10 years or so, and really arguably the last 5 years. Previously, when we measured system performance, we used point estimates. We'd say, oh, how's the system behaving? Well, the mean travel time is this, or the 95th percentile travel time is this, or it's congested, or it's not. So we were using very simple metrics to measure how our system was performing. And in the US, in the last 5 years, we've had this concept of travel time reliability. And so I'm going to use TTR as an acronym for travel time reliability. People are not only interested in point measures, but just trying to measure how the system is working. And I'll explain this further in the next few slides. So the Federal Highway Administration defines travel time reliability as the extent of unexpected delay to drivers. Okay. And the definition they use is the consistency or dependability in travel times as measured from day to day or across different times of the day. So their argument is if you get a lot of delays, you can travel every day, but you have one day where there's a large delay, that's more important to people than just what the average is. What I want you to notice from this definition is there's nothing very quantitative about it. Consistency, dependability. These are qualitative terms, not quantitative terms. There's a major research program called F-Sharp program that was been funded over the last 5 years. They define TTR as a variation in travel times over a time period. For example, an hour, or day-to-day variations. And for the grad students listening and have taken statistics, variation, that means, changes over time, but it's a qualitative term. It's not a quantitative term. Okay? It's just a describing something, but you can't say, well, here's a definition of variation. There's lots of definitions of variation, and I'll come back to this in a few slides. The Highway Capacity Manual. And so for those of you not familiar with the US, this is the major design guide for the United States when we're doing roadway operations. Okay. Arterials, highways, freeways. If you came to the United States and took a course in traffic flow or ITS, we would be using the Highway Capacity Manual models a lot. Okay. So it is actually one of the top manuals in the United States for designing and operating roads. They define travel time reliability. They say it reflects the distribution of trip time over an extended period. So remember, reflects, again, is a qualitative term, not a quantitative term. And they say it's a function of weather events, incidents, work zones, special events. The latest version of the Highway Capacity Manual, at the HCM6, just came out, and for the first time, they have a travel time reliability estimation methodology inside, and I'm going to talk about the arterials. So they've actually created a way of measuring and estimating and forecasting travel time reliability in our design guide. And this just shows you how important it is from a national perspective that we're now designing and forecasting, estimating these concepts. This slide shows the procedure, and I don't want to go into a great detail on it. You can go to the HCM6. It shows this diagram, but basically they take a bunch of scenarios. They look at demand, they look at weather, they look at incidents. They have a data set, in this case an arterial roadway. How many lanes does it have? How many traffic signals? What's the timing? And they do a bunch of scenario analysis and they evaluate the travel time. And the key part to this graph that I want to get across is at the bottom, their procedure creates a travel time distribution. And so you can see there's on the x-axis is number of trips, y-axis is number of trips. On the x-axis is travel time in minutes. This is just an example. And they create this distribution. They say this is an estimate. If you're looking at a previous year, if you're looking at a future year, it's a forecast. But the key is that they're using a travel time distribution. And from that, they create performance metrics, planning time index, buffer index. I'll be talking more about this in a few slides. But the key is they recognize the need to have a travel time distribution if they want to talk about how reliable something is. So in the past, we may have said, what's the average time? Or what's the 95th percent time? In the future, what we're doing now is we're looking at relationships between the spread, how wide is this distribution, and what the mean of the distribution or the central tendency is. Where's the middle of this distribution? And I'm going to be coming back to this again and again. So I wanted to show you that the Highway Capacity Manual is doing this. I'm going to take one aside right now. So I'm just going to step to the side as I talk. The question is, they just put this in, does the HCM work? So I said earlier, we have really good data here. We have years of data on our roads because we have these test beds where we've been collecting data. One of them is North 27th Street. And we can look at travel time as of value over 15 minutes average travel time, we can create our own distributions empirically. So we have years of data on our arterial roadways in our city of Lincoln, Nebraska, and we can plot them. So we said, oh, let's take the HCM method, see what it does, and we'll compare it empirically. So the blue is what we find happening in our city. These are the blue over the years. This is the cumulative density function. This is the travel times. The red is what the highway capacity manual says for our city. And you can look at that and say, boy, those are very different. And that's what we found. We did it for this corridor. We ended up doing it for 6 corridors. We could never get it to work. It was off by 80%. You just couldn't get the spread. So what HCM 6 was saying was that our city arterials were really reliable, not much spread, and we were getting the opposite. So we actually went to Transportation Research Board meeting. We went to the meeting, we talked to the people who developed it, and we asked them some questions about it. It turned out they put this method into the HCM and they never validated it. They never checked it against any empirical data. It was all a simulation model, basically, a Monte Carlo simulation model. We've since gone in and calibrated the model so we can actually replicate our numbers, and we're encouraging the HCM to do similar things. But it is an interesting concept from a research point of view that you can develop something, put it in your design guidelines, and actually it doesn't work when you look at it empirically. So lessons learned. What I wanted to get across in this, no longer measure performance by a single measurement. We do mean and 95th percentile. Reliability, when we talk about travel time reliability, it's a function of the travel time distribution. Could be a mean, could be median, could be variance, 95th percentile. And there's no clear definition, at least in the US. We have not developed a clear definition of what travel time reliability is. And then as an aside, just for everyone, validate your models, right? So HCM6, we thought that it had been validated, it hadn't. So if you're ever using a model, I always encourage my students to go and get data and compare it and see if it's working. Is it behaving the way you want it? In this case, it was pretty invaluable for us. We had a couple of graduate students. One of them won a paper award at TRB for actually showing what I just showed in the previous slide. So travel time data collection in the US, as I indicated before, previously it was all government, speed detectors, loop detectors. Right now we've gone to private sector. I talked about streetlight. There's a number of them out there. In this talk, I'm going to use INREX. It's just one more company that gathers this data and provides it out. You can buy it. In our case, our state government buys it, so we have access to the data. So let's get back to the COVID-19 pandemic. It's actually a natural experiment. Did the pandemic result in more reliable arterial roadway travel times? Well, we can answer that. We can look at it and say, what are these metrics that they have? Or did they actually capture that? Are there better transportation reliability metrics? And this is what I want to end my discussion with, or my talk with. So we went out and got travel time data for our areas, for our arterial roadways. We looked at AM and PM peak. We looked at 15-minute subperiods. We looked at average travel times. And we looked at when the pandemic first hit, which for us was March, April, and May. We got it for 2020, and then we got the data for 2018 and 2019 so we can compare it. So we're looking at the question, did reliability increase or decrease with the COVID-19 pandemic? We looked at 4 corridors. I'm only showing one here. This is Omaha Dodge Street. It's about 3 miles long, 80,000 AADT, level of service F. So we were looking for 2 to 3 mile corridors that had fairly high traffic in the peak periods. We looked at 4 corridors. We looked at 2 peak periods and 2 directions. So we're looking at 16 scenarios or 16 travel time distributions. Okay? So we're looking at 16 different things that happened in our state. Here's westbound Dodge Street AM peak. So one of the 16 is this one. On the y-axis is the 15-minute travel time. On the x-axis shows March through May of 2018 in gray, March through May of 2019 in blue, March through May in 2020, the pandemic year. These are box plots. The black line in the middle is the median. The two bars showing the box are the 25th and 75th percentile time. The other bars are the 5th and 95th percentile. The dots are outliers. Okay? And when you look at these box plots, a couple of things should note. The median went down, the central tendency went down, so travel times dropped. Makes sense, we have less traffic, travel times are going down. The other thing that's happened is the box plot's narrower, so our spread of travel times has gone lower. Okay, so there's less variability in travel time. And the other thing you can notice is we're getting less outliers. Okay? So lower mean, lower spread of travel times. You can also show that, so the mean dropped about 17%, the standard deviation dropped 47. Okay? So the spread got much, much smaller compared to the mean. So the mean travel time's dropping, the variability is dropping even more. You can draw a cumulative density function, same thing. The red line is 2020, the blue and gray lines are 2019, 2018. Again, we're getting a drop in, it's the same data showing it a different way. The mean is getting smaller and the variability is getting tighter. This is O Street. We westbound O Street, AM peak. Same type of box plot, same type of things that you can see. In 2020, the travel time decreased. In this case, about 17%. The standard deviation had a bigger decrease, about 55%. Okay, so the travel time is getting lower and less variability, and you can see it, less outliers. Similar, you can do it on a cumulative density plot, same data. When the red line moves to the left, that means the travel time is getting quicker. When it's tighter, when it has less variability, it's a straighter line, and you can see the same types of things going on. Now, we did this 16 times. I'm not going to show you the other 14. I just wanted to show you in general what was going on. But I will say for all 16 had similar relationships. The mean went down, the standard deviation went down more. So here are the 16 scenarios. The mean went down on average of 14%. The standard deviation of travel time went down about 44%. The coefficient of variation, which is the standard deviation over the mean, went down about 34%. So what could you conclude from this talk? Well, the travel times became more reliable. I said, well, did we get more reliable travel times? And the answer is yeah. Regardless of your definition of what reliability is, your mean went down and your variability went down. Our arterial roadways were more reliable. And you'd say, well, we expect that. You have less traffic, they should be more reliable. And they were. What I want to do now, though, is just talk about how we measure travel time reliability in the United States and why this experiment is important. So the US transportation agencies do not use common statistical metrics, okay, up front. So they don't use these to measure reliability. So they do, you can get mean, you can get standard deviation, COV. Their argument is if they do that, the users won't understand what they're doing, okay? What I just showed you, the users won't understand. So they went out and created a wide range of metrics. Travel time index, planning time index, and I'm going to talk about these next. The travel time index that they use is the mean travel time over the free flow travel time. So really, how much more time will I need to travel the corridor compared to free flow conditions? If the TTI is 4, it means your travel time is going to be 4 times longer than free flow. Yeah, if it's 10 minutes, it's going to take you 40 minutes. If it's 5 minutes, it's going to take you 20 minutes. If I calculate this for our example, the average decrease was 14%. It's the same as the mean. And it is. So instead of using the mean travel time, they created a travel time index, which is essentially the mean travel time divided by a constant. Comparing them is the same as comparing to the mean travel time. Planning time index, that's the 95th percentile travel time over the free flow time. The question this answers is how much more time will I need to travel the corridor and be less than 95% of the travel times compared to free flow conditions. So it's really what's the worst you're going to do. You know, if you follow this one, 95% of the time you'll be okay. 5% of the time you'll be late. The difference, it dropped about 20% along our corridors. Level of travel time reliability is the metric they came up with. It's the 80th percentile travel time over the 50th percentile travel time. The important one about this, it's actually used by the United States Department of Transportation to measure how well their national highway systems perform. Okay? So if you look at the 80th percentile travel time and divide by the 50th percentile travel time, from 2020, the pandemic year, compared to 2018 to 2019, okay, and this is their measure of travel reliability, it went down 3%. Why did it only go down 3%? Why was there only a 3% change? It's because the 80th percentile travel time changed at about the same way as the 50th percentile time. So the actual metric was not picking up any change in reliability. So if you were looking at this, you'd almost say there was no change in reliability if you were using the US standard definition of travel time reliability. The last one I'm going to do is the buffer index. They came up with this. This is the 90th percent travel time over the mean travel time divided by the mean travel time. What this is a measure of dispersion. How wide are my distribution divided by a measure of central tendency? What's my average at? If you look at the equation, it's very similar to the coefficient of variation I showed earlier. The difference was about 34.3% for the 16 quarters we looked at. The COV was essentially the same because they're measuring the same thing. So our government, the FHWA, says users can't understand the COV, but their argument somehow is that they can understand the buffer index. Lessons learned. So the question I started with, are the arterial roadways more reliable because during COVID times? And if you look at it, you're going to get a number 14, 20, 3.1, 34.3. These are the metrics we use in the United States to measure reliability. So the answer is, what metric are you using? If you're using LORTR, you'd say there wasn't any change in reliability. If you're using the buffer index, you'd say, it's about 34% change, right? 34% more reliable. So, like anything, what metric you use sometimes affects what your answer is. The second lesson for me is, my suggestion when we're looking at these is use the travel time distribution directly, right? That told us more. When I looked at the distributions, that told me more of what was going on than looking at these other metrics. If you're going to use metrics to do reliability, remember that it's a function of both. It's a measure of central tendency, the mean or median, whatever you want to use, a measure of dispersion, standard deviation range, interquartile range, whatever you're talking about measuring. And you really, if you want to understand reliability, you have to look at both. So either pick the distribution or pick the two things that are of interest to you. Trying to pick one metric to measure two things can get you in trouble. Right? So again, we have this, in the US, we have this real desire to measure something, get one number and say, this is what it is. But if it's a complex thing like reliability, one metric really might actually lead you to making an incorrect conclusion. Our proposal here is that we should use the standard techniques, statistics, where they're well known. We can develop formula, we get confidence intervals, and then we can take that information and provide it to the drivers. Because I agree, most drivers aren't going to know transportation statistics, but they are interested in what time should I leave for work, how long would it take me to get to the next interchange. We can answer those with the statistical analyses. So concluding remarks, COVID-19 had a profound effect on the transportation system. It actually was a natural experiment on how do we measure our system performance. Crash rate went up, are we less safe? Travel time reliability, I showed a case where it's the same, right? With this level of travel time reliability, even though I don't believe it is. So the lesson, reducing complex systems to simple metrics can be misleading, and always know your data, know your statistics in order to make meaningful inferences. And with that, I want to acknowledge my research team. Dr. Ernest Tue is a postdoc here who's done a lot of work on reliability. Sean Murphy is a master's science student here, and both have done extensive work in the reliability research. And with that, any questions? Dr. Secchi, I think one of your grad students has fallen asleep on me.
Well, that's not very nice. Well, if the audience doesn't know, that's how I used to look when I was in Waterloo.
It was, I think it was when that photo was taken when you were asked to do another rewrite of your PhD. So.
Yeah, this is a very old picture.
Seems like yesterday, Jose.
Yeah, time's flying. Well, I have a question for you. I found it very interesting when you said about the need for calibration of models. And I would like you to elaborate a little bit more on that, because I think this is something very important for graduate students in transportation engineering, to calibrate the model so you can make conclusions that are really based on something real. And I find it very interesting that the comparison that you did, that the models are incredibly different.
Mm-hmm. Sure. So what you know, and this is very typical in engineering. So it's a great question. And again, my focus wasn't on doing this is a whole other, obviously, series of presentations, but I did want to get across that the reason this was important to us is that when we're talking about travel times and you're trying to model things, if you're very interested in reliability, you have to have a travel time distribution. If your model is not giving you the one you're observing, you have to make changes. So if you were doing this by hand, if you were calibrating by hand, you might come up here and change something about the way they run their model, right? They run a model and they get a distribution. So you may change your assumptions, you would do something. If it was a simulation model, you'd change how far the cars are following or something. So, you know, when Dr. Secchi and I when we were students, we would do this by hand. We would change something, see if we could get the spread out, get it back. Now we do this automatically. We can set this up in a computer program, and we literally can do thousands, tens of thousands of changes. So we can use genetic algorithms or search algorithms, find the changes that get that red diagram to match the blue one. And that's essentially what we would do, is go through, change the, in our case, it was changing the demand. That was the one we were interested in, the demand factors, to get the spread out so we would fit it. But it's very typical. So this is a case of reliability. If you're using a simulation model and you're trying to do delay and you're not getting the delay you want from the field, you can change the parameters in the simulation model so it actually matches what you're doing. So on our focus, when we're talking about validation, calibration, we're interested in travel time distributions. So we were changing the model inputs so that the red, which is the predicted travel time, was matching the blue exactly. We had the same mean and we had the same spread. So that's a long answer, Jose. Did I answer your question?
Oh, yes. I have another question for you. The question's from Leandro Marcomini. He's a PhD student here in our program. And he's asking, do you think these effects of on travel time will disappear right after we solve the pandemic problem? Will we have any good side effects from the pandemic?
Yeah, it's an excellent question. And of course, you know, everyone is hypothesizing what's going on. We've already seen in our state, we're almost back to normal in terms of movement, certainly freight movements for sure. What we're not getting is other ones. I think we're going to see changes in how people behave, in the sense that we have a lot of people working at home, and I think that it might, we're not all going to go back to work at work in the offices. Is sort of my prediction. I don't know if that's true or not. Certainly, we've always talked about telecommuting and working from home, but I think that so many people are doing it now. Maybe not everyone's going back. If you can show they're as productive at home or remotely as they are in the office, and particularly in the U.S. because it's so expensive to live in some of the cities on the coast of the United States, Seattle, San Francisco, New York. There's already been a push to move people to the cities that don't cost as much in the center and work remotely. So I think we'll see some changes. I certainly expect that to go on. We'll see how fast it rebounds. I think from the perspective of this talk, I'm hoping that it changes the way we evaluate things or measure things. Because I said, when you're changing 1 or 2%, sometimes the metrics you use don't capture things. But when you get a 30 or 40% drop, you'd sure like your metrics to be able to work for that. So I'm hoping from our perspective that some of the stuff we talked about here will get implemented. Thank you.
Another question that I have for you is about those indices that measure as you showed us. And the interesting thing is that the index that the FHWA uses, the level of travel time reliability, is the one that's most insensitive to changes. And we could see huge changes. And so you have to be very careful about creating indices, and because you might shoot yourself in the foot, right?
Oh yeah, so I have two. Yeah, I agree 100%. And to me, I have always had two issues with the U.S. FHWA and their approach. The first was that we have this great history and we have these great statisticians, right, who spent years looking at distributions in general. They don't care that it's travel time, but they know these things very well. And so to say, forget that, we're going to develop our own, never made any sense to me. And when you do that, I think the lesson is you can cause yourself a problem. And in this case, I think I know exactly what was going on. They wanted to relate 80th percentile because it didn't change as much as 95th or 100th percentile to the mean, right? Because most times it's a little bit wider, which makes sense, except if you have major changes in what you're interested in. So I agree with you, Jose. I think you want to really identify, if you said what is reliable, to me, something smaller travel time is more reliable. I would say that, and less variability. And you want to look at both individually and then together rather than trying to put it into one index and saying, here's my answer. Because otherwise you get answers like this, which are, to me, counterintuitive. And I think to most people would be.
We have another question here. This one is from Raquel Carneiro. She's a master's student here in our program. She's asking, can we use data from COVID times to calibrate models? How does this affect the analysis of level of services?
Yeah, that's an excellent question, and you certainly can. So one of the issues in fact, it would be a good thing to do. One of the issues with calibrating models is that your model is only good for the data you calibrate it to, right? So in this case, you could imagine taking 2019 data with your volumes, taking 2020 with a 40% drop in volumes, and making sure that your model works for both. That in this case, let's say you're calibrating the travel time, that the mean and distribution were the same in 19, and your model also got the correct mean and distribution in 20, then you'd have a much better feeling that if you were between those volumes, 20% lower or 10% lower, you'd have a lot better, you're interpolating rather than extrapolating. So A, you can do it, and B, it would be a good thing if you expect it to be between those. And as almost any of your professors will tell you, if you have a model and you start extrapolating too far from what you've calibrated to, you're probably going to run into trouble. It rarely works.
Yeah, I think it's a good opportunity to change obtain data that can you help find the frontiers of like the envelope your model to see how far you can go with your extension of results when you have this huge variation, right? There is another question here. There's this questions from Orlando Strandi, who's a professor at the Polytechnic in São Paulo. I think you met him in a conference in the past. He's saying measuring travel time reliability is a complicated business, but predicting it as a result of interventions in the transportation system is even more complex. What are the advancements on this topic?
Yeah, that's an excellent question. So in the U.S., as I said, let me go back, right? In the U.S., the newest one for arterials is the HCM method. As I said, they use this for forecasting, and as I said, our experience has been it doesn't work very well. Forecasting is always difficult, but I think it goes back to what we've found and what we're doing. So I'll talk about our research on this problem. Is we have almost gotten away from using deterministic models. We're using much more simulation models as the engine for predicting these travel time distributions. But we spend a lot of time, just as you were indicating, Jose, making sure that the distributions that are coming out match what we're, the empirical ones match what we're doing in the simulations, right? That we can replicate what's going on. And if we can't, we're not very confident in it. And it goes back to the earlier question. If you want to forecast, you better make sure that your bounds or your envelopes are correct, that your model is correct for the bounds that you're forecasting for, right? So if your demand goes up 20%, you have to be very confident that your model can capture that and reflect it in the travel time distribution. Because if you can't do that, your model is not going to be very good and it's not going to get very good results. And the problem comes in, it's almost like this. The problem is actually shown what I showed here. You can take a model and run it, right? And in this case, you can run it and get that red distribution. If you never check it, right, you can always get the distribution, say, I have a model that gives me a number, but if you've never checked it against anything, it really doesn't provide you much help. And so our only solution to the question is really do lots of different scenarios and make sure that the changes that you put in this case demand, actually are reflected accurately in the model. And if you can't do that, you're going to have a trouble with your forecasting. But the questioner is absolutely 100% correct. This is a very difficult problem, particularly when you go from estimation to forecasting.
Well, they have a saying that forecasting would be, if forecasting would be easy, all the economists would be millionaires, right?
That's right. We'd be out of a job. So yeah,
yeah. I mean, it's hard business trying to discover the future, and I think that many times. But I think the model is when you have a model that's well calibrated, at least you can do some analysis of what could happen if this happens, but as you said, within the limits of that we know that the model is valid, right?
Yeah, and I think
we have another question. Those are two questions that I'm going to put them in just one because we're starting to run out of time. They are from Ellen Miranda. She's a PhD student in our program. She says the changes in risk behavior are quite impressive. Are there the same behavior, the same changes observed in urban centers, or you only have data for highways? And the other thing that she's asking is how the government are going to handle this incompatibility in the increase in the aggressive behavior and the rise in bicycle use, because I think the bicycle users can be put in danger by those increasing risky behaviors.
Yeah, so excellent questions. I don't have the data with me. My understanding that it's everywhere in both urban and rural settings and highway settings in terms of the risky behavior. And I think it's across the, this is a output of society, not part of the transportation, just something that's reflected in the transportation system. So it's a societal issue. Obviously, the way they're handling, it sort of indicated, the way they're handling it in our state and our cities is there's a lot more enforcement in terms of everything, speeding. So people are driving faster, speeding. There's a lot more enforcement going on. So it's kind of ironic. Volumes are down, but there's actually more enforcement because of the dangerous driving. There's more enforcement on seatbelt regulations. Again, because these crashes are just too many already. So that's sort of the solution. The bigger answer is societal, right? And I think it's kind of ironic when we're talking about COVID-19. We're talking, oh, this is great. We have all this data. We can do all these models. It's one of the few benefits I've seen to this pandemic, right, is that we can do this. Thing is horrible. And I think we're all looking forward to getting it over so we can get back to normal lives. Excellent questions. But there is really there's no simple solution that I've heard other than I know that our police officers and state patrol are doing a lot more enforcement than they were doing a year ago.
Well, I think we finished with the questions. There's lots of people thanking you for the excellent presentation, and I would also, on behalf of the two programs, two graduate programs here, the program in São Carlos and the program in São Paulo, Polytechnic in São Paulo, we would like to thank you for giving us this very interesting presentation, and it's food for thought, because I think you can learn a lot from what's happening now, and it's very interesting. Well, thank you.
No, it's my pleasure, and I actually look forward to seeing everyone in Brazil, hopefully very, very soon.
Yes, as soon as we have a vaccine.
I can't wait. So everyone stay safe and stay healthy. Thank you.
Okay, thank you.